So from last Wednesday, we introduced you the state pattern, right? Let's review what the problem really is that we're trying to solve. Okay, so this would be an example of the problem we're trying to solve here. All right. Basically, if you can somehow formulate the behavior of your system using a state machine, finite automata, okay? That's what you learned back in 2001. Since most of you learned it, I assume you have the technique of drawing the state machines. Okay, so that's kind of the state transition diagram we have for this particular system, okay? Basically, every time, if you can actually draw the diagram for the behavior of your system, that means it's a very good candidate for the state pattern. And every time, if you have a tree structure, like a hierarchical structure for your objects created at the runtime, what would be the pattern for that? The one we learned just before the state pattern, which is composite and visitor, right? By the way, lab number 5 was released. Did you notice that? That one is about composite and visitor. It's quite a fun lab, actually. For those of you who are interested in taking, for example, in the 4th year, so there's a course called 4302, I believe. It's called Compilers and Interpreters. It will give you a little bit flavor about compiler, a little bit, okay? Anyway, lab number 5 is quite a fun lab, so do spend some time in that. Okay, so that's the diagram we just went through last time. We're going to revisit this diagram again very soon, okay? Let me remind you very quickly. So that's a problem we are trying to solve. And it's really important for you to really criticize on other alternative solutions. For example, the very first solution we had over here, basically you just got labels over here with actions, right? It's going to work, but we say that it's going to suffer from reusability, single choice principle stuff, right? That's something you can review quickly, okay? That's a very first attempt. You can just implement it using C, for example, or assembly language. It's quite a low-level solution. You don't want to go there. It's too ugly. Solution number 2. I want to talk about it together with the final solution. So this diagram here really illustrates conceptually how you should compare the non-OO solution, the hierarchical solution, versus the OO solution. So these are the two. Okay, basically we're considering, let's say, the non-hierarchical solution over here. Basically at the top level, we already went over the code last time, so I assume you can just go back. I just want to highlight to you quickly. It's like a top-down approach. We got execute session over here, which is going to execute the interaction between the program and the user for as long as it might take. And then it's going to be staged into 4 different stages, especially for one of them is called execute states. So to really execute a session, remember the problem we were talking about. You want to know where you are in the diagram conceptually, right? You might be in state number 2, or you might be in state number 5. It's a state-dependent behavior, basically. Okay? So now, to execute the states, we have to take as a parameter, the states information over there. And then from execute states, you're going to have different stages over here, right? For each stage, you simply just have to say, if the current state is number 2, for example, you're going to display differently from if the state is number 4. Okay? Good. Wow, guys, a little bit interesting. You guys are quite active today. Well, but still no comparison to 1021 class. You guys are fine. Okay, doesn't bother me too much. Okay, so huh? Of course I can. You mean about the passing a parameter, right? Why don't we do it again? Actually, it would be a very good question for you if I simply give you the second solution. I would say the first one is quite a no-brainer. It's definitely worse, right? But you really want to see how we make a transition from the solution number 2 to the state pattern. It's really important, okay? Let me just show you the critical code that you should really pay attention to. Let me just go over slides, since we already went through the iPad, so I wouldn't go into details, right? That's going to be time-consuming. What I would do is I'm going to go right away to the second solution over there. Good. Okay, fine. Okay, now the top-down hierarchical solution over here. So we have a transition table. That's something we assume. Okay, you can easily implement it using a 2-dimensional array. Okay. So now what we want to really look at is exactly this structure over here. Okay, I tell you what, this part here is really easy. This part simply just interact with the user. And then execute state is going to say, depending on what the current state is, we're going to have a template to say, for each state, we're going to display, and then read, and then validates, and then output some error message if applicable, and also to process the input. Girls? Hi. I can almost hear what you're talking about, almost. That's okay, that's okay. Yeah, almost, not quite. Okay, so now for this second solution over here, okay, let's have a quick look. And then we'll see how to move a transition from there. Okay, so now that's the execute session, that's the top level. Okay, we talk about execute session over here. Okay, execute session over here. If you talk about it, we simply say, basically, you have some initial states being some integer. Actually, you know what? One thing to note, in the case of the second and third solution, we are using integer to somehow represent the current states, somehow. However, in the third solution, using a state pattern, we actually use the integer as index into some polymorphic array. That's something additional, which we haven't seen so far. That's something we'll get into today. Okay? That's a critical thing. But in both cases, to start with, you're using integer to represent the current states. And then we say that we're going to interact with the user until we reach a terminating state. And for every state, we simply try to execute the states, which means depending on what the current state is, do some state dependence behavior. Okay? So now this is really important because you can see we are passing the current state over here. Let's do a comparison right away. In the second solution, you have to say execute states and give current state as a parameter, right? What about the third solution, the state pattern? You do have an execute feature there as well. But now the current state is no longer the input over there. It's the context objects, right? So let me show you very quickly. If you look at that over here, if you look at the hierarchical non-OO solution, you can simply say execute session and current states is simply an input parameter, right? Okay. So now eventually, what we really want to change that into is something like this. Now when we declare current states, we simply say it's simply a states, objects, all right? And then what we can say is we can simply use the current states as the context objects right now. So that means you can simply say execute session. It's a very, very important paradigm switch. First, make sure you're comfortable with this is switch over here. The bottom there in the yellow is not using any OO. You can program that with any language that supports a procedure like a C. Okay. The number 2 over there in the green above is really using a context object, which is OO. Okay, it's a very important change in the paradigm. Apart from that, let's talk a little bit more about what's really wrong with the second solution. While passing around the thing, passing around the current state, it can still work. I agree, it can still work. But again, we talk about design, not just working implementation in this course. Let's see what's going to happen if the state is actually passed around in every stage at the third level, the level 1, according to the diagram. So what I would do is, let's see exactly, okay, execute states is simply just going to call different helper methods. It's going to call the display, read answer, and also read choice, and also correct. One thing to know, later on when you review the state pattern for exam, okay, there's something I want you to do again. I want you to really compare the execute states feature in the second design versus the execute feature in the third design, the state pattern. You will see that they're basically the same, except the following. Let me see if I do have the code for that one. Let me see if I do. If I don't, I will mention that briefly to you. Okay, let me go a little bit further for you. Okay, basically, again, we talk about 2 different designs. So we're going to talk about non-OO solution versus we got the OO solution, which is a state pattern. Okay, so now let's see this. I want to give you a little more insight. Okay, so now let's say for the non-OO solution, we simply got, let's say, execute session over here, and then over here we simply got, I'll say CS standing for current states. Okay, and that is simply of type integer. I'll say int for now. And then let's see somehow like this. Basically, over here, what we are including here is like a pattern of interaction. For example, you want to say, I have a loop to say until I got a valid answer from the user, I'm going to display, re-answer, re-choice, correct, and message, etc. Right? Let me just put two of them. Let's say display and re-answer. Okay, bless you. Okay, so over here we got display over here, and then it's going to be taking current state, right? That's a very important thing to notice. And also we got, let's say, read answer. I'm just omitting the loop over here, just for simplicity. Okay, that's the first design. Okay, so now let me draw a separator over here. Okay, so now I'm going to use another color here to illustrate. Okay, so now how about start with blue first? In the OO solution over there, so now since we got OO, we got classes. What we will do is we're going to first of all have a class called states. Class states. Okay. Now, when we define the feature that's corresponding to execute session in the second design, we're going to say execute. And notice that no parameters needed. In the Java case, you got this, the context object, right? Implicit this. In Eiffel, you got current, which is a current object you're calling the feature, right? That's something very important. Okay, so now if I say execute, and then I will say do and end. If I want to have the corresponding thing, I will simply say display, and also read answer. So now, can you see the difference over here? Syntactically, the only difference is basically the second design, I'm simply using parameter CS, which is referring to the CS over here. But now, in the case of the second design over here, you can see no parameters needed, simply because implicitly we have current as a context object, current, implicitly. That means later on, when you're trying to be the clients of the state pattern, what you will do, for example, you might say S1 dot execute versus, let's say, S2 dot execute. Right? When you are trying to execute this particular feature call, context object is not S1. So that means current will be replaced by, current will be, over here will be replaced by S1 and S1. So it's going to do S1 the display and S1 the re-answer. Which version of display and re-answer will be called depends on the dynamic type of S1. Agree? Similarly, when I try to do over here, let's do one more. When I try to execute S2 the execute, that means we're going to consider S2 the display and also S2 the re-answer, right? Things will just work out in the OO way. Okay? That's a really fundamental insight for you to get into. Okay, let me say one more thing about the second design. Okay? At the same time, we're also reviewing the third one. So now let me say a little bit more. So now the important issue is which design principle is the second design suffering? Single choice principle, but of course you know that from last time, but if I want you to explain exactly how it is going to violate, you make sure you know how to do it. Okay? Basically, every feature over here at the middle level, at the bottom level, level 1, is going to take the current state as the parameter, right? So that means you have to do some exhaustive check on what the value is. If you actually got 6 different states in the diagram, in the system, you need to have 6 different branching conditions. If you got 10, you need 10. If you got 100, you need 100. It's very tedious to do, even for just one time. Like you do it multiple times. Okay, so now that's kind of what you have to do. And exactly how it violates single choice principle, every time, if you want to see your design is good or not, you want to really argue to yourself whether my design is fragile to changes to my design, right? For example, what kind of change can I make to the second design? If I want to add a new state, for example, that means rather than having 6 states, I'm going to have 7 states. So that means for every feature, display, re-answer, validate, etc., I need to add an extra else if to say else if state number 7, right? So that's a violating single choice principle. Similarly, if I want to say I want to shrink down the state space, rather than having 6, I want to have 5 states only. In that case, I got to delete maybe one of the else if statement in every place, right, for the feature. That's what we said last time. Okay, it's okay. So now, any questions about this? Second design, yes. Uh-huh. No, actually, the truth is you don't have to. We'll actually see a little bit more code. I guess your question is, do we still need any kind of if statement to check to see? No, we don't have to. That's really something I'll make a conclusion again to show you. Okay, and keep that in mind. The really big advantage of using the OO solution is you never have to use any if then else statement to exhaustively check which state I am in. You don't have to. Dynamic binding is going to do it for you. Okay? Yeah, we'll get there, don't worry. Yeah, that's definitely the most important insight you want to get into for this state design pattern. Okay, so now after that, so we talk about the state design pattern. Basically, anyway, the conclusion for the second design is basically this. Let me just show you again over here. If you look at the diagram for the second design over here, because the state is actually passed all over as an input, to make it OO, you simply make the state itself a class called states. And then every feature that we're supposed to really execute, they will just be relevant features in the state class. Okay, that's something you will see. Okay, that's pretty much where we left off from Wednesday last week. Okay, but let's talk about the architecture again very quickly, and then we'll see a little bit more development code. Okay, and then we're done, and we move on to a new topic. Okay, again, this is a design diagram for you. Every time you want to review a design pattern, try not to look at the code too much. Look at the design diagrams. Because once you understand the architecture over here, you can easily translate it into any other language, right? Of course, IFO has the advantage where you can write contracts for your features. Otherwise, to just get a working implementation, a design diagram will be enough for you. Okay, let's have a quick look, and now we'll highlight the important stuff for you. Okay. So now let me just go to a bigger diagram over here. Okay, this one here. Okay, that's the architecture for the state pattern over here. Basically here. Okay, that's the architecture. So we start with the clients over here, which is some application over here, right? So we have a client-supplier relation over here to just the top-level defer class called states. Number one. Okay. So what do we have to define or declare in the state class? Okay, let's see exactly what's going to happen here. So now you have read, display, correct, process, and message. All these features are declared as deferred, which means they simply don't have any implementation at the state level. We just simply don't know. For example, for the read feature over here, for the read feature, we simply don't know whether that should be the read for initial, the read for help, the read for final, and etc. We simply don't know. That's why we simply leave it as deferred at this level here. Okay? And then for, it's very similar to, for example, accept feature for the visitor pattern, right? So that's something you are required to do for lab number 5. Okay, so these are the 5 defer features over here. And then notice one thing. This one is really important. You can see that the execute feature over here is plus. That means that feature there is implemented. Okay? However, the way it is implemented is by referring to the defer features. That's an interesting bit. You do have something corresponding to this for your lab number 3. I'm going to leave you to that because that could be covered in the exam as well. Think about the correspondence over there. Okay? The same design pattern over here, which is called template. I'll review again. Okay, apart from this, you can see we got basically initial flight inquiry. We got this many descending classes. Each one of them is simply effective. Think about what they have to declare, what they have to define. Okay, notice one thing. For this one here, let's say for initial, all you got to do is you have to really implement the read for initial. I need to implement the display. Okay, and also I have to implement correct. Let me write it down. Correct, and also process, and also message. Everything that was deferred at the state level, I'm obliged to actually implement this in every descending class over here. Apart from one feature, execute, I don't have to. I simply inherit that verbatim to the descending class. Okay, we'll see exactly how that works. Okay, and that's something I talked about last time over here. Okay, so now we'll talk about exactly how this is going to work after I show you a little bit more code. Okay. Any question about the architecture over here for the state pattern? Any part that's not clear to you? Okay. So basically, now we're going to see, first of all, how to declare and define the state class, and then we'll see how exactly these features will be declared or defined. Okay, that's what we're going to see. Okay, now we have a deferred class states, okay, which means we can never create an instance directly from that. Okay, and then we got read, that's deferred, right? Also we got answer, that's also deferred. Also we got, answer is simply some attribute over there for us to store the answer for the result. And also we got also choice, also some, so for answer and choice, so these are simply some attributes to store the input read from the user. Okay, as far as the pattern is concerned, they are not that important. Also we got display, and we got correct, and we got process, and we got message, right? Let's count. We got read, display, correct, process, and message, right? The 5 features that's deferred. And this simply just corresponds to the 5 blue features here that's deferred, right? So now we want to look at how exactly the execute feature looks like. That's the important part, okay? Now we got execute feature also in the state class. Remember, for a class to be deferred, you simply follow the same rule for a class to be abstract in Java. For a class to be deferred, you got at least one feature that's unimplemented, just at least one. Okay, so now we got, for sure, you can, for example, the read feature is not implemented, right? It's deferred. Now for the execute feature, it's going to be effective, which means that we do have implementation for that. Let's just go over the structure very quickly. Basically, we're going to have a Boolean just called good. Basically, we're going to interact with the user, keep executing until we got a good answer from the user. Okay, the same idea. And then call the display. Question for you. At this level here for the states, is display effective or deferred? Deferred, right? That's okay, it still works. Okay? What's going to happen is, imagine that for every effective descending class of states, the display will be effective, which means we're going to call that version specifically. Okay? And then I'm going to display, and also we're going to read. And also we want to say whether the answer the user enters is good or not by following the validation process called correct. And also we're going to say if it is not good, answer from the user, we'll actually give some error message to the user. Okay? And then eventually, once we get a good input from the user, we can process the current states, right? Okay, now let me switch to iPad very quickly for you. Okay, now if you look at exactly what we had just gone over, so now it's worth doing some illustration over here. Okay, so now what I will do is I'm going to first of all highlight all the deferred features. This is deferred. This is deferred. This is deferred. This is all the blue features are deferred features, which means at this state level we simply don't know how they should be implemented. They should be state dependence. What about the execute feature over here? That's effective. Okay, now here comes the important thing. So the execute feature over here is effective. Okay, I simply call this as it's so-called the template pattern, because you can think about this is simply a pattern of calling helper features. How about that? That's how we compose behavior together, right? So now I want you to look at exactly how we call the defer feature over here. You can see display, we got read, we got correct, we got message, and we got process. You can see inside this particular effective feature here, we're calling defer features. That's absolutely allowed. Okay, are we okay? It's a really important thing to note. So now what we want to know is exactly what's going to happen at the runtime. Okay? So now let's think about this. I will just want to draw a quick diagram here. Okay? So again, we have our state class over here that is deferred. Okay? And then let me just, again, I'm going to just use these two features as an example. Okay? We know that execute is actually effective. That's a template. And also we got display that is deferred. Okay, let me draw a little bit better. Okay, the display is deferred. And also we got read, that's also deferred. Okay, that's a top class. Let's just find two descending classes only. Okay, let's say I just do, let's just think color, that will be okay. Okay, the first class, let's say seed inquiry, and that one is effective. Okay, and then we also got confirmation. Okay, confirmation. Okay, so we got these two effective classes. Now let's see exactly what will be available to them. For sure, because these classes, they are deferred, they are effective. So that means you are required to implement all the inherited features that are deferred. Specifically, you can see the display and read. So now the display will be implemented as one version. And the display over here under confirmation will also be implemented differently, right? Although they are both called display. And also we got read over here. And also we got read over here. What happened to the execute feature? Well, that was simply inherited unless you decide to redefine that. You can definitely do it, but for the state pattern, we don't have to. That's why it's called template, which means we reuse the same template that's defined at the state level for every descendant classes. Okay? So now what I can do is I'll just put in parentheses. You can think about the execute is going to be inherited verbatim over here. Okay, so you can think about inherited. Okay, that's kind of the conceptual layout over here. Let's see exactly what's going to happen at the runtime. Okay, so now let's try to execute this block of code over here. Okay, let's draw a little bit. What I would do is, first of all, let's see this. So now we declare S to be of type states, the static type. Okay. So S at the runtime can point to any objects that is a descending class of states. In this case, it can be either of the 6 classes over here, either one of them. Okay. So now when we try to execute this particular line, we say create seed inquiry. That means now S is going to point to a seed inquiry objects over here, right? So now what's going to happen if we say S.execute? So what's going to happen exactly? Okay? If we do that, first of all, which version of execute is going to be executed? The version that we're going to execute here, where is that defined? In the state class, right? Okay, there's only one version over here. So execute over here is going to be the version in state class that's inherited verbatim. Now, if we try, let's say we're going to execute this particular feature call for the first time, right? This particular feature for the first time. Now, when we get to display, and when we get to read, for example, now, which version are we going to call? Seed inquiry, right? Because now we know that dynamically, this is the object that's pointing to. And now we know that it's going to call display and read from the template. Dynamically, it's simply going to call display and read from over here. Okay, that's going to call that. The execute, the template, there's only one version at the state class. However, the helper feature it call is going to be defined at the subclass level. That's going to be called because of dynamic binding. Yes?
If you redefine execute like in the inquiry,
yeah.
and you call s.make, would it call the
Good question. Yes. The question is, if you try to redefine the execute feature, let's say in the seed inquiry, yes, it's going to call that version instead. Okay, sure, you might want to do that. But remember, once you do that, okay, basically what you're asking is this. Let me first of all tell you what's going to happen, and then I'll question you. Okay. So now let's say this. Again, you're saying that we got states over here, and then we got already one version of the execute over here. Let's say we got seed inquiry, and also we have confirmation. Okay. What you're suggesting, number one, I'm going to redefine the execute feature. I'm going to say plus plus. Okay. And then that means over here, the confirmation is going to inherit this version verbatim, right? So now let's have a quick look. If I say S, again, is of type states. And then if I say creates seed inquiry S.make, That's fine. If I say s.execute, okay, and then I'm going to say creates. Okay, let's make a little bit more space over here. Okay, it creates, and then we got a confirmation s.make, and then I say s.execute again. Okay, so now let's compare it specifically these two lines. Okay, so now what about the first line? Which version of execute are we calling? The C inquiry, right? Exactly this one here, right? So this one here is calling it execute the redefined version. Okay, what about the next one? The top, right? Because for dynamically it's confirmation, but confirmation has not redefined the feature. So it's going to be execute that version there. That's the runtime behavior. But now the question is, why would you want to do that? You can definitely do it programmatically. As soon as you do that, you got now two versions of the template. One is shared by all the other states except for C inquiry. And one template is only used by C inquiry. You can never decouple, right, all the states from each other. So I would say in theory you don't need to do it, right? Although in practice you might do it. Okay. Okay. Any questions about this? As you can see, we keep emphasizing the ideas about static typing, dynamic binding, those stuff, right? Okay, so now if I go back here, we'll see the code a little bit later. Okay, and then after this, yeah, you can just follow through the other two, right? Once we change the dynamic type to be confirmation, so now dynamic type will make sure when you call to execute, it is still going to call this particular version that has never been redefined. And then dynamically, when you call display and read again, it's going to call these two versions instead, right? Okay, that's really about the runtime behavior between the states, depending on what their dynamic type is. Guys, any questions? The tricky thing about this part over here is we got two patterns working together. We got state pattern, also we got template pattern working that. You define template only at the ancestor classes that can be shared. So template can be shared. Okay. If no question, we want to see a little bit more code. Yes? Oh, we will get there, yes. So let me ask you one question here. According to, let's say we only got two states over here. We got C inquiry, we got confirmation, right? So now where should you define? Well, and also display and read, they are deferred in the state class, no implementation. Now how many places do you have to define the display feature? How many places? No, I'm just saying the display and read. What I'm asking is, according to the architecture over here, we have two deferred features, display and read, right? So where should they be defined? Yeah, exactly. So either both in C inquiry and also the confirmation, right? That's exactly you got to do it. Yes. I wouldn't show you the complete details because how you display is completely up to your application. But my point is, you have to make sure these two deferred features must be made effective in both classes, depending on how you want to implement them, right? Okay. But now and then, when I make a conclusion about the pattern, we want to see why we can get around with if statements by checking the dynamic type. We'll get there. Okay.
What the requirements for processing message? So here you have processing requires correct and message not correct.
Mm-hmm.
Your template here you have good equals correct, not good. But at the end of the from you have cross.
Mm-hmm. Sure. Basically, yeah. This one as a minor point, but sure. Let's talk about it quickly. Over here, you can see, let me talk about message first, okay? If you look at the message over here, it tells you, you know what, in some way that's good, because somehow you're trying to get a sense about the behavior of the feature by looking at the contracts. That's good, right? That's why contract is really powerful. So now we say that in order to really give a message, you require that the input that's being entered by the user is not correct. So that means the message we're displaying is error message, right? If the user entered a right credit card number, you shouldn't bother them with some error message, right? So we are saying if the answer is not correct, message, okay? On the other hand, if you look at the other feature, which is process, process could be, once I get a valid credit card information from the user, I want to charge them. But if the credit card number is invalid, should I bother initiating the charging process? I shouldn't, right? That's why it should require that to be correct. Mm-hmm. Yeah, if you look at that here, yes. If you look at that, message is actually called under the condition that the user input is not good. So that satisfies its precondition, right? No. The process over here, okay, one thing to note. You want to identify where the loop is, right? This part is the loop. Agree? So that means when you only do the process not as part of the loop in the iteration, you only try to do the process outside the loop, right? So what does it really mean when you're outside the loop? You can look at, well, that's something we'll talk a little bit more towards the end. We'll talk about how you can prove the correctness of a loop. Okay, let me just give you a little bit intuition here. Over here, we say that we will keep running the loop until the user's input is good, which means if we stay in the loop, that means the user's input currently is not good. As soon as we exit from the loop, that means the user's input has been validated, they're good. In that case, we can go ahead and process. So logically, it makes sense. Yeah, we'll get into about proving the correctness of the loop towards the end. You don't have to worry. For now, since you have used the from until or cross loop, so just use them. Okay? But we'll talk about how you can formulate some correctness property for your loops. We'll get there a little bit later. It's not a focus for now. Okay? Any more question about what I'm showing here? Okay, quite many things over here. Just make sure you're comfortable. Okay? Okay, so now after this, let's do a little bit more. So now we want to, okay, that's exactly what I just illustrated, so you can read through the slides as well. So we talk about the template. It's really important to see how exactly the template works at the runtime. Okay, so now this is something like a preview of what's going to happen here. Okay, basically the way the state pattern works, you only need a fixed size of the array. Well, let's say at least to begin with. The size of the array corresponds to the number of states you might have at the runtime. At the moment, remember the state transition diagram, we got 6 different states. That means we got 6 different state objects at the runtime. Okay, you might switch between them, make a transition. For example, if I want to make a state transition from initial to reservation, all I gotta do is to say I'm gonna switch from index 1 to index 4, for example, to reservation. Okay, that's something we'll see. That's kind of the visualization you want to have. Well, we have 2 attributes that we're going to see. We're going to have some application objects for which we define 2 important attributes. Number 1, we define the states, which will be just an array of states. Remember what we said before, an array of expression, an array of students is polymorphic, which means every element in the array can just be a descendant class of states. In this case, we've got 6 different states according to the hierarchy, right? And then the transition over here is a transition table that we talk about. It's simply just going to be a 2-dimensional array, just integer. So there's exactly a transition table we'll talk about. We're going to see exactly how these 2 attributes will work together, okay? Let me give you a quick intuition, and then we'll get into the code. Every time you want to make a transition, let's say this. Let's say I'm currently in state number 1, okay? State number 1, which is in the initial states over here, right? Let's say let's say the user want to take action 5, okay? Action 5. I'm in state number 1, row number 1, and the user action number 2, that's what I meant. I'm now in state number 1, the user want to take action number 2. That tells me I should go to the target state being 5, right? So that means I should really switch from state number 1 to state number 5 over here, which is confirmation. That's kind of the switch I need to do throughout the lifetime of the application. That's something we'll see. Okay? Before that, let's see a little bit more code from the application, and then we'll trace. Okay, so now we're basically done with the state pattern. We're done. Okay, but now we just want to see how to use it. Up to now, we talk about a supplier for the state pattern, but now we talk about the clients, how we can use it. So let's just go over very quickly the attributes and features you want to support, and it was trace one test code all together with you. First of all, we got the transition table, which is an array, two-dimensional array of integer, right? The transition table. Basically, think about how you're going to implement a state pattern. Always, you want to draw the state diagram on a piece of paper to start with. Identify all the states, and then you can code the transition table quite easily once you define the state diagram on your paper. Okay, so we got transition, which is an array of integer. And then this is a polymorphic array that we talk about, right? So that means every element in this particular array called states is going to be a state object, polymorphic, right? It can be initial, can be confirmation, can be seed inquiry, etc. Now we have some, the way we actually represent the current states, we use also use an integer over there, okay? We simply say initial over here, and then the number of states, depending on what your application is, it can be 6, can be 10, can be 100, can be 1,000. Also, we got number of choices is like a number of transitions, right? How many possible outgoing transitions you might have, for each state. Okay, so now to make this very easy, you simply just initialize the attributes. For that part, I wouldn't bother you. You can just try them out to see how to use them. Now, what should be the invariants? That's an interesting bit. Invariant basically tells you under what circumstances are the application going to be in a valid state, right? I will give you a little bit of hints. What kind of constraint do you have to impose based on the number of states and the number of choices? For example, what should be the relationship between these two variables over here? For example, let's say, for example, the number of states over here and the number of choices, should they constrain any of the attributes over here? Should they? They should. Give me some answer. Informally, that'll be okay. Should be the dimension. The range. Oh, actually, let me take back. You say the number of states and the number of choices should be the size of the states, but the states are one-dimensional array. I was going a little too far. Sorry. Let me say it again. So you're basically talking about a constraint on the size of this state over here, right? But the size is only one number. But which number should it be constrained to? Number of states, right? Right? Because you want to say the number, the length or the count for this states array should be exactly the same as the number of states, right? Yeah. So for example, if you look at the diagram, I'll show you the diagram actually quickly. If you look at the diagram over here, so this is a states array. The size of that should be exactly the number of states you have, right? In this case, just 6. Okay, that one's easy. What about the transition table? Number of choices should be the number of columns or number of rows? Columns in this case, right? Because you can see we got 1, 2, 3, 4, 5, 6 that correspond to the number of states. Each one of them may have either 1 or 2 or 3, right? The choices, right? Okay, that's a very easy constraint you can put into. Okay, so now just make sure everything consistent. Okay, you can use the height and you can use the width. Okay, good. Okay, after this, let's do a little bit more stuff. Now you can also try to put in some states. Okay, so now what does it really mean to put the states? Basically, let me show you quickly the feature, and then we'll do things together quickly. Okay. Basically, you can put the states, and now you want to make sure the index should be valid for the states array. Okay, and then just put it. Okay, you can use the force feature. I'll show you exactly how that works. And also, you can choose the initial states over here. Given some index that's valid, you can also choose it. Okay. Okay, and also you can put a transition. This one is also interesting. How exactly do you put a transition into the two-dimensional array? Given the target states, given the source state, and given the choice, okay, you want to make a transition. Okay. That's okay. All the 3 features, I'm going to show you exactly how they will work. One thing to know, when you review this particular layout, when we say put transition, we first put the target states, and then the source states, and then the choice. Okay, we'll get there. So now what I want to do is I want to go over some example test together with you quickly. Okay, and then we'll see how exactly things will work. Okay, what I would do is I would go on over here, okay, and try to see how things work. Well, the diagram here is already showing the final outcome, right? The final layout. But let's just let me link to you how each bit is actually created by the code. Okay. Okay. If you look at the local variable over there, we got app of type application. Okay. And also the current states is simply of type states, which means dynamically the current state might be storing any objects that's descendant class of states, right? Let's get it clear. And also we got index. The index over here, you can think about index is more like a pointer to say if the index is currently pointing to, let's say, position 3, that means the current state should be C inquiry. If the index is pointing to index 5, that means the current state should be confirmation, okay, etc. Just keep that in mind. Okay, let's see how things will work. First of all, when we say create application.make, okay, it tells me the number of states should be 6, and then the number of transitions should be 3. So you can see we can create different applications quite easily. So what this will do is it's going to make sure we create an array of size 6, from 1 to 6, right? Initially, it simply store nothing inside initially. And then we also try to create a table over here. The transition table is going to be 6 by 3. You can see that's exactly 6 by 3. Okay, that's what we'll do. But nothing has been put so far into the array or to the transition table. We want to see exactly how you can do that quickly. Okay, it's not that bad. Okay, after this, let's see how do we put the states. Let's just see one example over here. Okay, first of all, you can see that the put states will take 2 inputs. The second input tells you you should put whatever state object you're creating into this particular index. In this case, the index 1. What should we put there? You want to put an object of type initial states. Okay, create an initial over here, and then let 1 point there. And you do the same for every other 5 states. Okay, for example, you might create flight inquiry and store that into index 2 into the array, right? Do something similar. Okay, for that I don't need to show you anymore. Are we good so far? Okay, just put in the states. And then we'll also choose initial over here. Okay, choose initial to say initial state should be the state at index 1. So that means you can think about initial over here is somehow just pointing to this particular object that's at index 1. Okay, that's what that means. Okay. And then we're going to put a transition. So this is the interesting bit. Okay, I'll show you quickly. How do we initialize a transition? Initially, you can think about everything that's stored over here is simply just 0 initially. Okay, I'm just put 0 here. Nothing has been set up. Okay, just like that. What does it really mean when we say app dot put transition? Put transition and then 6, 1, and 1. What that means is if you're currently in state number 1, that's the current states, source states. And then I want to take this particular action. My final state should be at 6. So now that means I should really go to row number 1. If I'm taking action number 1, the corresponding value should be 6. I put 6 over there. Okay, it's just a convention we have chosen. Basically, the convention we have chosen, when you want to put a transition there, put the final state, target state first, and then where you are, and also the action you want to take. If you're the designer for this feature, feel free to change the order of the parameter, as long as you're using that consistently. I'm just trying to point out to you, for this particular example I'm showing in the slides, we follow this. Guys, question for you. Can you tell me exactly what I need to write as an exercise quickly for you? I want to store the following transition here. If I'm currently in the reservation states, I want to say that if I actually go to, the user takes action number 3, I should go to confirmation for the pink one. Okay, help me out. If I say app dot put transition, right? What should I put? 5. Okay, the target state, right? And then 4, and then 3. Okay, we're just using that convention over there. So I'm saying that if I'm currently in state number 4, which is over here, if I take action number 3, I'm going to go to state number 5. Okay, good. So now let's do a little bit more. Okay, so now let's see. So the way dynamic binding is going to work, we have seen that already. I want to put that into more context over here. Now, index, which tells us where the current state should be, initially it's simply just 1. Okay, initially it's simply just 1 because we chose that to be 1 initially. Okay, so that means the initial is really denoting the first object over here in the array. So now let's have a look. I want you to pay attention to these lines. First of all, this one here. Current states, which is of type states, right? Is assigned to application, which is over here. That's the object that states, which is referring to this array over here at index. What's index in this case? 1. Index 1 is referring to this particular initial object, right? So now, if I try to say attached initial is really like an instance of check, right? That should be true. Similarly, at the moment, if I simply try another one, okay, I'll put it down here. If I simply say current states dot display. Now, which version of display is it going to call? In the initial, right? Because we know that the current states is really referring to this particular object dynamically. So when you say current state.display, it's going to call the display defined in this version over here. Okay, that's how we make a transition. Okay, so now let's do another one. If you look at that, so now let's say we want to go for the transition table over there. Okay, we simply go to app.transition. So app, again, transition is referring to this transition table over here, right? Let's assume we already, let's assume we already correctly filled out all the transition over here already, let's say. Okay, that's transition table. So now if we want to make a transition over here, let's say I simply say index, that is current states. We know that current state is simply just 1. So that means we should look at line number 1, row number 1. And then the action we take is simply just 3. In that case, what should be the target state? That should be 2, right? So that one is going to give us back 2. So index is now going to become 2. And now we can do the change accordingly. So now, once we know the index is 2 after the state transition, we can now say the current state is simply assigned to app states at index 2. Okay, if we try that, so now, where does the current state refer to now? Index 2, you can see index 2 is exactly flight inquiry over here, right? So that means current states is now going to refer to this particular object here dynamically. Okay? So now when you try to say result.attached flight inquiry, it's simply just going to be true dynamically, right? One more thing to show. If I say current states dot display, which version of display is it going to call? Flight inquiry. Yes, because dynamically we are really pointing to the flight inquiry objects over here, right? Okay. Yeah, we're okay. So now we're basically talking about the same subject here, except that I'm just trying to tell you eventually you have to have some application class that will make use of the state pattern. Okay. Any questions? If no question here, let's make a final conclusion slides about the state pattern before we move on to a new topic. Okay. Okay, so that's exactly what we said over here. Okay, actually this one here, this one is simply just about application. We got one more about execute session. How do we define that? Okay, I'll show you very quickly. So we got the current states, we got the index over here. Eventually, you'll simply say assign some initial states to be any number, and then we'll simply say until the state is final, right? Some terminating states. Every time we'll simply say current states is assigned to the states at index. Okay? So now we want to make sure we want to change the index by doing some transition table lookup. That's an integer. Okay? And then after that, once we get a current state, we can simply call execute on that. So now you can see that that's exactly where the OO solution stands out. You don't have to say execute with the parameter current states. You can simply say current state execute. right? Good. And then by the end of the iteration, you got to make a transition as well to change the index. Okay, basically just switch between. You might be starting with initial state over here. You might change to reservation, and then you might change to C inquiry. You might change to confirmation. You just keep changing, right? But the binding for the current state might just change. But static type, it just states. Okay. Okay, so now here I just summarize exactly what you got to do if you do the application as a client. Okay, everything we have gone over, so I don't need to repeat. So now finally, we want to just compare again design number 2 and design number 3. So these are really important comparisons for you to understand. Okay, so now in the second solution over there, we have to explicitly and manually discriminate on the current state input. We want to say if the current state equals 7, do something. If the current state equals 2, do something, right? However, in the state pattern there, we don't have to do this to any extent. All we got to do is to make sure inside the descending class of the state, let's say C inquiry, and then we define the display feature over there. And then the dynamic binding is just going to work out at the runtime. Okay, what we're going to do is, okay, exactly. So you're going to say display and then the current states. You're going to say display 1, display 2, right? But now in the OO solution, no if statement will be required. So that means you have no chance to violate the single choice principle. So now what you're going to do is you're going to say define the states, and then you simply call s.display, right? Depending on what the dynamic type is for s, you're going to execute differently. Any questions? Are we good? Any confusion? Any thoughts? Good. Is it too easy or too hard? I think the former should be the case, right? That's good. All right. Applying that, of course. Guys, one very common misconception is if you think you understand 100% of the lecture, it's a good start, but it's not sufficient. It's necessary, but not sufficient. So in order for you to do well in the exam, or let's not talk about the lab tests, it's gone. To really do well in the exam, not only that you're going to understand the lectures, you want to be able to explain the same issues. For example, if I just give you one quiz right away, I want you to criticize on the second design. Are you able to write it on the paper? Right? If you think so, yeah, good. But if you don't think, yeah, maybe not quite, that means you still got some gap over there. Okay? To really do well in the exam, you want to make sure you are able to reproduce many of the explanations I made in the class, especially to explain how dynamic binding, static typing actually work, right? So if I give you something a little bit different from what I show in the class, you will be able to judge to see how to solve it, okay? We can talk a little bit more in the review session later, but for now, you may want to start preparing for the exam if you have time. Okay, so now let's move on to a new series of lecture. Okay, that's about the state pattern. I did make available some source code to you, the one we talk about in the class. Okay, you can definitely look it up in the lectures page. Okay, you can play with them. Okay. So what I would like to do now, I would like to move on to some new lecture series about subcontracting. We got at least one more design pattern to be discussed, which is called observer pattern. So that one, again, is going to make use of polymorphism, dynamic binding, and we're going to talk about event-driven programming as well. That also got the, if you program in C#, for example, they got something called delegates. In Java, they got something called lambda calculus, lambda function. They do have some correspondence over there, but I will just show you in one language for this course, right? Everything can be transferable. But before that, I would like to talk about subcontracting. You may have noticed that for your lab number 1, 2, and 3, some contract is not just called ensure, it's called ensure then. And some contract is not just called require, it's require else. The answer is, in the context of inheritance, we want to somehow ensure substitutability, right? When we talk about this word substitutability was back in the inheritance lecture, right? For example, let's say, if I say S is of type students, now what can I substitute students by? Any of the descending classes, right? For example, it can be resident students or non-resident students. The intuition is any subclasses got at least as many code as in the parents. So that's why you can always substitute the descendant instances for the parent instances. Okay? But now we want to see exactly how you can do this in the design by contract context. Okay? The idea is not that bad. I'll just give you an example to show you. But this lecture can be a little bit more logical than others. So we're going to do a little bit logic. Okay? Simple logic. I'll warm you up. I'll make you warm up before we talk about the actual example. This is a very quick review slides. So when we talk about inheritance, again, what you learned back in 2030 and also before the reading week is mainly just about code reuse. Okay? How you can reuse the methods and also about substitutability, polymorphism, dynamic binding. Okay? That's what we have covered so far. Okay? These are compile time check, right? Now, subcontracting is something very interesting. Somehow you want to specify the contracts at the subclass so that you will ensure substitutability. Okay? But that's something we'll get into. Okay? Runtime behavior checks. However, you really want to understand because of substitutability, when we say you accumulate a contract in the subclasses, how do we accumulate that? The way you accumulate invariance, the way you accumulate precondition, and the way you accumulate postcondition, they're different. Okay? You want to see why they're different. You don't just memorize. There's a logical reasoning behind, okay? Which we'll go through. Okay? Let's do a little bit of logic for the background. Very easy logic, just to make it much more comfortable for you later as well. Let's say we got two Boolean conditions, P1 and P2, or predicates, right? It can be x larger than 0. It can be y larger than 2, for example, right? Just any Boolean condition. Let's say we have two preconditions, P1 and P2. Okay? Let's define some terminology here. We say that P2 require less than P1. So somehow the precondition P2 require less than P1, right? So what does that mean? That means P2 somehow is less strict by allowing more inputs than P1 does. Okay? So now, how do we formulate this? Actually, can we just do one example here, okay, before we get there? Okay, so we talk about require less, right? Now, let me just move this guy here to here. Be easier for us. Let's say we got some feature over here. Let's say square root. And then we got x of type integer. Okay? So now let's say we got two possible preconditions. Let's say we got P2, or let's say P1 and P2. Okay? So now let's say over here, x greater than 2. P2, x greater than 0. So now let's review the terminology quickly. I hope I got the name consistent. I hope. Let's see this. Okay, over here we got two preconditions, P1 and P2. I think I did it right. Okay, I say P2 require less than P1. Because if P2 is less strict by allowing more input than P1 does. How do we see that over here? Think about let's imagine how you can think of this. If I say P2 is going to be x larger than 0, what would be the allowable input values for x? What would be the first one? Not 0, right? I heard some 0 somewhere. Maybe, okay, anyway. It can be 1, can be 2, can be 3, and more. This one here, do we get more or less? Less, right? We got starting from 3 and then all the way through. Yes? It's a very good question. Basically, it's another orthogonal issue. So here we just talk about when you given P1 and P2, can we say one is more tolerant or allow more when we're given two preconditions, can we actually say one require less than the other? Which one should be correct is another story. You're absolutely right. In this particular case, let me say this, okay? That's absolutely right. We can say P2 require less than P1 because we allow 1 and 2, whereas P1 does not allow. Okay, that's number one. And now P1 versus P2. Which one is correct? I would say it's up to your design decision. In the case of square root, maybe we want to calculate as many square root as possible. In this case, maybe P1 would be a little bit better. Oh, sorry. In this case, maybe P2 would be a little bit better. So we can always calculate as many numbers square root as possible. But in this case, you're saying for P1, you're saying that I cannot calculate square root for 1 and 2, but why not, right? I would say the first one is about which one require less. That's the most important lesson to learn from this particular lecture. And number 2 over here, which one should be correct is up to your judgment, okay? Sometimes maybe both are okay. It's just about whether which one might be more acceptable by your clients, okay? So now, are we okay with this? Okay, good now. So now let's go a little bit further. Okay, for those of you who want things to be a little bit more formal, when we got P2 and P1, how can we formulate to really see why P2 require less than P1, right? Why do we have, let's say, x larger than 0 require less than x larger than 2? Why is that? Basically, this is how you can think of it. You can think about with all the values that is going to be satisfied by x larger than 0 is a set. What about the corresponding set for x larger than 2? It's going to be bigger, smaller, or intersecting? It should be a subset, right? Actually, they do intersect, yes, okay? Something like this. X larger than 2. And we know that, for example, outside the orange part is you got 1 and 2. Okay, that's conceptually how you can think of it. Of course, when predicate gets more complicated, you want to be sure you can also draw it to clarify yourself. Okay, so now we know that basically the bigger the set is, the more tolerance or the less the precondition require. Okay, now if you look at that, so now this is one way to think about how you can formulate it. Basically, don't be too terrified. Everything has been learned back in 2019. You're basically saying for all the value x that's being satisfied by P1 versus all the value that's being satisfied by P2, the set for P1 is a subset of the set of P2, right? That's exactly what we're drawing over here. So this is the set for P2, and this is the set for P1. We're saying P1, the set for P1 is a subset of set for P2. Okay. So now, can we be a little bit more concise? Well, actually, back in 2090, when you prove subset relationship, right? How do we prove a subset? If I want to prove that this subset relationship holds, what can I prove instead? Using one of the logical operators. Huh? Implies, yeah. If you got implies, in this case, should we say P1 implies P2 or P2 implies P1? You should follow the direction for the subset relationship, right? Okay? Okay, so I assume you pick it up from 2090. If not, speak to me. Otherwise, you'll be in trouble later. Okay, more concisely, you can say P1 implies P2. Basically, you can think about, when we talk about predicate implication, it corresponds to subset relations. So we talk about satisfying values for the both predicates. Okay, go a little bit further. Whenever, if you're given P2 and P1, both are preconditions. If you say P2 can be implied by another one, that means P2 somehow is weaker, logically weaker. And so P2 can actually require less because it contains more possible input values to be allowed. Okay? That's the first slide. Okay? Okay, I just got another example for you. Okay, you can see P2 is amount larger than equal to 0, just non-negative. In that case, it requires less than amount strictly larger than 0 because P2 allows also 0, but P1 doesn't. Okay, just one value different. What is the precondition that requires the least? Let's go extreme. What would be the biggest set that's going to contain all the possible values for the input? True? Yeah? Yeah. So the weakest precondition you might have is called true, which means any input value is going to satisfy that. You'll never get a precondition violation for your clients. Your client will be very happy with this feature here because anything they try to pass will be okay. Not necessarily good for the supplier, but depends. Okay? Yeah. Huh? We'll get there. The reason that I try to introduce you about one precondition require less, and also what is the weakest precondition here, is because later on, after the first two slides, we're going to talk about the keyword require less and ensure more in IFO. That's something we'll get into. Well, not just about IFO, it's more about precondition and postcondition in inheritance. Okay, we'll get there. Okay, that's about this one here. And then let's do another one. So now let's talk about postcondition, okay? In the previous slide, we just talked about precondition. So now for the postcondition or invariance, let's talk about postcondition only. Let's say we've got Q1 and Q2, okay? So now we talk about if I say Q2 ensures more than Q1, okay? This one can be a common misconception over here. What does it really mean? When I say a postcondition ensures more than the other, it simply means it's harder to satisfy this particular Q2 over here, right? Because it's harder to satisfy it, so now the corresponding set of values that satisfy Q2 should be smaller because it's harder to satisfy it, okay? Okay, so the diagram, the way to draw it, I'll draw that in just a moment once we see the example over there, okay? It will be very similar, okay? So now let's try this. So now you can also formulate using a subset. You want to say Q2 is somehow stronger, right? Because it's harder to satisfy Q2. So whatever that satisfies Q2 is a subset of what satisfies Q1, right? And more concisely, you will say Q2 implies Q1. Later on, you might be, let me give you the preview. What will you be given eventually? What you will be given eventually is, I will give you an inheritance hierarchy. Let's say I got class 1 and also subclass C2, C1 and C2. And then I will simply put preconditions, a precondition in the superclass, another corresponding precondition that's redefined in the subclass. I will ask you to judge logically whether it's correct or not, okay? So the principle is, whenever you have a precondition in the subclass, you should require no more, or you should require at least less than the parent class. Okay, that's something we'll get into. That's why we're going to talk about all these before we can get there. Okay, so now let's have a look at that. So now let's say we got Q2 and Q1, okay? Think about this, even though I already gave you the hints. I'll put the two things on the iPad very quickly, okay? I want you to look at these two predicates over there and then try to see why one is going to ensure more than the other. Okay, just give me 1 more minute, a few seconds. I'm just going to write it down. Okay, that's also a very common pattern over here. Okay, we got Q2 and Q1 over here, right? Now, should it be the case that Q2 implies Q1? Or should it be the case that Q1 implies Q2? Okay, 1 or 2? 1, right? Everybody agree? Well, we can try, okay? By the way, it can be both, right? If that's both, that means they're equivalents. Apparently they are not, because you can see one is using conjunction over here, the other one is using disjunction, so they cannot be equivalents. Okay, let's agree on that. So now, what's really Q2 is saying? Q2 basically say result, well, it's a Boolean query, right? It's going to be if I must be positive, and also I must be even number, positive even basically. Okay, if you think about it, something like this. It's going to be, let's say, 2, 4, 6, 8, 10, etc. What about Q1? Is Q1 going to be a subset of Q2 or bigger? Bigger. Give me one example that's in Q1 that's going to satisfy Q1 but not Q2. 1, right? For example, if I give you 1, 1 definitely is positive even though it's not even. That's okay. It's disjunction. Or I can give you, for example, -4, right? Minus 4 is going to make this false, but modulo 2 will be 0 anyway, right? Okay, so you can see that one is bigger, so that's Q1. Okay, and that's Q2. So this is a very important skill, minimum skill you should really have later. When I give you two predicates, you want to know which one is going to be stronger and which one is going to be weaker. Okay, it's very important for you to know. Any question about this? For this one here? Yes. Yes, that's also possible. Yeah, I think for this course, we give you the most common one. So most likely, it's going to be that one predicate is such a subset of the other. Okay. If not, of course, you don't have the implication. Mm-hmm. You're separate. Yeah. Mm-hmm. Yeah, we'll still do the simple example first. Okay. Basically, whenever you're trying to design the pre or post condition for your child class, you want to make sure somehow it has some logical relation with the contract in the parent class. Okay, that's the point. You don't want to have something that's totally irrelevant. Okay. Okay, we still have a few minutes. Okay, let's do a little bit more. Oh, actually, so what's the post condition ensures the most? Well, false. But now, intuitively, what does it really mean? When you have a false post condition, basically you say ensure false. In some way, it ensures the most. In what sense? It's so restrictive, nobody can ever satisfy that. It's so high standard, you can think about that. Doesn't matter how good you are, you just don't satisfy that. Okay, logically speaking. Okay, okay, that's good. We'll just go extremes over here. So now we talk about inheritance and contracts. We'll do maybe just some slides here, and then maybe on Wednesday when we start, we'll go through the example. Let's go a little bit slides over here, and then I will show you some architecture here that should clarify. So now let's go back to our familiar example over here. We got smartphone, and we got different dynamic type, right? Basically, you can see that. Let me review very quickly for you. What we did previously, we declared my phone to be smartphone, which is the top of the hierarchy. Dynamically, well, of course, we can do different assignment, which is polymorphic. So now, when I say iPhone is assigned to my phone, we know that the type checking rule tells us we can do that because the static type of iPhone 6s Plus, is a descending class of smartphone. When it is descending class, that means we can substitute some iPhone 6s Plus for the smartphone. What does that mean intuitively? If I'm expecting a smartphone to be purchased, you can give to me as a supplier any descending class of a smartphone. Right? In this case, any of the descending classes, iPhone 6s Plus, Galaxy, or HTC, they all work. Okay? That's a very quick review of the polymorphic assignment we talked about before the reading week. Okay, so basically we can substitute a subclass for some parent class. Okay, because the subclass accumulates at least as many code as the parent class. And then we want to make sure, okay, here's constant intuitive principles over here. Whenever you're trying to define contracts for the subclasses, either you're trying to define invariance, precondition, or postcondition. So here are the principles. You want to make sure whenever you're expecting something, you are being substituted by something else. That something else shouldn't give you any shock. Okay, that's something I will elaborate a little bit more. So that means whenever you're trying to define the contracts, you want to make sure, number one, the descending class should not require more. Okay, we'll see that. Okay, this is the informal principle. And also the descending class should not ensure less. Okay, that's kind of the principle. But we'll see by some example. Okay, let me just go through one more diagram and then we will continue on Wednesday. Okay, let's get clarify some terminology over here. Okay, so now you can see that from the phone user's point of view. Okay, we simply say my phone is of type smartphone. That means we got a client-supplier relation over here, my phone, and then smartphone presumably can just be deferred. Okay, it doesn't matter. And now let's say we have a feature called get reminders. Okay, basically get reminder is simply just going to tell you, just give you a list of events that you should be reminded about for today, for example, right? And now notice one thing here. In the parent class, you got require, you got ensure. On the other hand, in the subclass over here, you got require else and ensure then. Now, on Wednesday, we're going to see exactly the following. Okay, let me just talk about this and then we're done. If I give you some precondition over here, let me call that, let's say, P. And then in the subclass, I try to give you another precondition over here, Q. How do I judge whether P versus Q are appropriate? Okay, so here's a rule. I'll tell you right away. The precondition in the subclass should be weaker, or at least equivalent to the for the precondition in the parent class. So that means we should really prove the following: P implies Q. Okay, that's for the precondition. Okay. On the other hand, let's say ensure over here I say R, and ensure that I say S. So now it's going to be the opposite. So what about R versus S for the postcondition? We want to make sure the postcondition in the subclass ensure at least much as the parent class, right? In that case, we'll simply say S should imply R. Okay, so these are the two predicates you want to understand. Of course, you can see it's hard to memorize this. You don't want to do that. Okay, let's try to understand this maybe on Wednesday by some example. Okay, I'll see you on Wednesday.